Okay, hey guys. So we're gonna go through some of the technical details about the technology. We got Nick here, who is not as technical as I am.
So I'll be asking the questions.
Yeah. So I'm gonna break down today. Should I do the consensus mechanism and why it's better?
Yeah.
I wanted to do Clove too.
Yeah. So
should I do that after?
Clove, consensus mechanism. No, but Clove's a big one. So touch on Clove.
Well, the blockchain's big deal too.
Well, yeah, no, still, but I like Clove.
Okay, we'll start with Clove. Clove is really easy to explain. So basically, there's this idea of atomic swaps. This is a good position because you can see my face.
Yeah.
All right. So the entire idea of Clove is that we need chains to communicate with each other without actually having some sort of trust associated with them. So it's the whole concept of atomic swaps. I'm not going to go into how atomic swaps necessarily work right now, but what I am going to do is explain why Clove is very interesting and what we kind of found out. And I posted basically a development update that's like, oh, we can hit all of these different chains now. Why is that true? And basically talk about it. So with an atomic swap, what it basically means is that if you do not know, Bitcoin actually has a scripting language, and it's called Bitcoin script. I think it's just called script or something like that.
It's good enough.
Stack. But basically, when you send a transaction to somebody, it's not like a little package that's like to somebody, from somebody, amount. It's not laid out like this at all. And so really what's happening is that there's a set of computer instructions that's being transmitted, and that includes a package. So you're going to have certain, what they're called opcodes or operation codes on the stack, and then this gets executed. So this is, let's say this is the script. This is going to get compiled down into machine code and then transmitted. And then all of the nodes are going to compute this script, and then it's going to become some sort of thing. So like, for example, multi-sig wallets. How do multi-sig wallets work? Well, that's not a normal transaction. That's a little bit different transaction. You can do like a 3 out of 4 or 4 out of 5, which means if you have 3 signers out of 4, it remits the funds. And the reason why this happens is because in Bitcoin, addresses don't hold the Bitcoins. It's really outputs. So like when you spend Bitcoin, it's like it goes from A's Bitcoin, it spends it, and now it's B's. And now B basically has this Bitcoin somewhere on the blockchain and can then use it to spend there. But basically, it's not like you have all of these Bitcoins in a wallet. So, great. Now, these are called UTXOs, unspent transaction outputs. So that means when you spend something, then it becomes unspent by the other person. So if I spend 1 Bitcoin to Nick, he then has the UTXO of my Bitcoin now, but he can then spend it. So atomic swaps are all about how do you create these UTXOs in a way that's trustless so that if Nick has Litecoins and I have Bitcoins, we can swap and essentially trade these UTXOs, which give the rights to those coins on the other chain.
Yeah.
So what's interesting is that if you say Bitcoin script has a few atomic swap features. So there's the atomic swap contract function, and then there's a few different redeem mechanisms. But what is very important is that this scripting language is not modified in derivative forms. So this Bitcoin script is the same on the Litecoin chain as it is on Bitcoin. The operations are the same, the machine code is the same, it's going to act the same. So that's very interesting because I only have to write 1 atomic swap contract. I just have to build the raw transaction and push it out into the blockchain, and then I can do an atomic swap.
So does this include all the tokens on Ethereum and all derivatives of the other coins, Stu?
Good question, Nick. So no. So right, basically this piece of the puzzle is all Bitcoin-related derivatives. So you're talking about Bitcoin, Litecoin, Bitcoin Cash, Bcash, Dogecoin, Hcash or Hshare, Zcash, Dash, all of those, and then all of those derivatives, like PivX is a Dash derivative, which is a Bitcoin derivative. So essentially, PivX still has the same scripting language as Bitcoin, which means we can do these atomic swaps on any of them. So that gets into the interesting part about decentralized exchanges, which, let's talk about the ERC20 tokens. So ERC20 tokens are using Ethereum, and so they have an ERC20 contract that every single token behaves the same way. So you can do a decentralized exchange with these ERC20 tokens, no problem.
Yeah.
But you want to use coins themselves, right? So essentially, if you can do a swap on one side, you're going to have a contract. And Ethereum is good because you can create these contracts, and the smart contracts are really easy to create atomic swaps. Which basically atomic swap is you put money in here, and then when somebody gives the secret key, they then get it, but the secret is only learned when the other side does the same thing. So it requires both parties to move the funds, and then it's good. So Ethereum's really easy to do that. And so it's the same thing with ERC20 tokens, are really easy to do that. That's why you have Ether Delta. So what you can also do is you can store the secret in one of these things, whether it's an Ethereum contract or an ERC20 contract, and then this is 1/2 of the exchange where the atomic swap will happen here, and then this could be Bitcoin, and it's going to happen here. So to answer your question, it's a lot easier actually to use Ethereum for these atomic swaps because the programming language is a lot easier, and you can do these ERC20 tokens too. So now you can trade Litecoin for whatever ERC20 token you want.
Tau
token, right? Until we migrate it onto our own blockchain.
Yeah.
But so this is the interesting stuff. This is what we're programming, and so we program this, and then we automate it so that essentially our smart contracting language on Cilantro is called Pact, and Pact does have an atomic swap feature. It's written in a different language, but it's robust enough to allow it, right? So now we have this is the Cilantro Tau chain, right? Then we have Bitcoin, we have Ethereum, and we have Litecoin. I don't know what Litecoin's is. I think it's like that. So basically, now with these atomic swaps, you can either swap with these directly, or just decentralized, you can swap with these directly, or if you have a Lambda app, the app plugs into here, and then now this chain can interact with any of these. So this is the whole decentralized exchange.
So are you telling me that all these chains can work together?
I am, Nick. Wow, what a great question.
Thank you.
So basically, I mean, what we're developing is an automated version of this. So some people might be interested in a decentralized exchange, but also these applications then can pull all of these different cryptocurrencies together. So if you're like a game developer or anything, right, not only can you pull in funds from, like for example, in a token sale, it's all Ether, right? You can pull in funds on Lambda from all of them because we have automatic atomic swaps between anything. So you can take Bitcoin, you can take Ether, you can take Litecoin, writing one app. You just have to write one app. That's it. You don't have to create an implementation for all of them because Bitcoin has the same implementation as Litecoin, and Ethereum is already having these smart contracts, so it's easy. So, you know, we write the code once for Bitcoin. It goes through all those like dozen or 24 chains. Ready for that too. Boom. So also you're going to have expands, Ether Classic, and Cubic, which I'm not sure. I don't really use those, but those also have solidity in them. And so you'll be able to trade those as well.
And this is really interesting for enterprises as well when they create private chains. For whatever reason they want to use. I mean, we're already talking with healthcare and all these guys. Being able to create their own chains that interoperate through the Cilantro protocol creates a lot of data security, easy use. So there's a lot of application in the, the corporate structure as well. as being able to accept these different chains.
Yeah, yeah. Because I mean, like you could feasibly then pay for anything using Bitcoin, and then through these applications. Maybe it's a real estate application, and then this real estate application has a representation of dollars on it, right? So then you can pipe these Bitcoins through here to here and do 2 atomic swaps, boom, boom, and now you're there. And this makes a lot of sense because if you say, all right, how many different altcoins are there? I mean,
At least 5.
at least 5.
At least 5.
So there's Bitcoin, Dash, Litecoin, Ethereum,
Zcash, Monero.
Zcash.
Monero.
Well, I don't know if Monero
Oh,
actually supported it. I have to do more research into that. But what else? Bcash, Bitcoin Gold, all of those fun derivatives.
Yeah.
Ether Classic. There's HShare. There's EOS. EOS will work. I just have to figure out the actual implementation of it because it's smart contracting, and let's say like Lisk. So Lisk is smart contracting too. Now these can all form relationships with each other. This is what makes it decentralized. Great. No problem there. So you get the idea. So with atomic swaps, this basically happens, and now this is great and everything like that, but we're looking at some way to make this a lot easier for people, especially as these new chains come apart, and especially because these applications are going to be apart, and these more obscure things. This all relies on the fact that these are the major coins. If you have an obscure application, you're going to want some way to actually still pipe in this cryptocurrency, and so we get rid of all this stuff. And then we have our decentralized public chain, Cilantro. So then this plugs in like that, right? And this is a decentralized network that's managing a lot of this stuff. And then suddenly, instead of forming a relationship and all of those different implementations, this is taken care of for you. And this will, because it's one single implementation, if a new chain comes in, right, let's say 2 years from now, it just has to make one connection rather than one connection with every single one. So that's kind of the power of the blockchain. So, any questions?
No, I mean, explained pretty well.
Okay.
So, yeah, pretty much with our protocol, you just got to plug in any new token or chain, and it just connects with the rest.
Okay. Yeah. So basically now it's how does the consensus mechanism work and why it's better than Bitcoin. So Bitcoin uses proof of work. Proof of work is essentially, well, let's step it back. 3 transactions per second. Why is it 3 transactions per second? If you take a block, the amount of information in a block is what, 1 megabyte, 2 megabytes, something like that. I mean, it's not that much data. And so you download more data than this every single second on your internet. You get like 10 megabits or something like that or whatever. It's more than a megabyte. But this takes 10 minutes, right? And every block has a difficulty target of 10 minutes. So it means that this takes 10 minutes to compute, right? What does that mean? You're paying a mining fee for this too. So people think, oh, well, when I send my Bitcoins to Nick, the miners do a lot of work to make sure it's legit, right? That's not what happens. That's not true. It takes like seconds for the block to essentially be produced and minted. It takes 10 minutes for the hash to be solved. And so we say from the mempool, which is all the transactions, we fill this block up. Yay. It has a whole bunch of transactions in it.
Sweet.
And then now what we'll do is we'll hash it. So this is the hashing mechanism, right? We'll do SHA on this. This is some math, so bear with me. Basically, when you hash something, it takes any size, whether it's 1 megabyte or 1 kilobyte, and it turns it into, it depends on the hash, but the one that Bitcoin uses is 256 bytes. It's a lot smaller, right? And so it's a lot easier to compare 256 bytes with each other to make sure that everybody's got the right information in 1 kilobyte and 1 megabyte. And why this is important is because you can't essentially fake a hash. So when you have this block, I want to quickly make sure with everybody else that this block is agreed upon. I can hash it, and then got 256 bytes. I save a ton of time, because otherwise I have to pass this with every single other node, a megabyte, and then I have to go through every single one and compute it. That takes forever. This is easy. 256 bytes, not a problem. That flies out there. Everybody essentially SHAs it and gets it out there. So let's say, for this example, we're working with SHA, and it creates a 3-letter hash. And this represents what this is. So if you have a different block, right, it's going to be a completely different hash. And then you know that these are not equal. Those aren't equal with each other. So this is the consensus mechanism. To determine if a block has the right transactions in it, and no one's hacking it, you have the network of nodes. These transactions go in and they're propagated throughout the network. And each of these nodes will just add it to their sort of log, right? And when consensus time comes, everybody takes that block, and it's a fixed size with Bitcoin. They'll hash it, right? And then they'll compare with each other what they got. So let's say ABC, 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 CDE, ABC, ABC. Cool. So now it's really easy to compare this. We don't have to look at what's inside the block at all. We can say, if you got ABC, you got it, because hashes can't be replicated. There's a concept of collisions where that does happen, but it's astronomically rare, and the chances of you producing a block that's valid inside of the Bitcoin protocol and actually is advantageous to you and maintaining a hash is like impossible. So you quickly go doot, 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 doot. This guy did something wrong. Whether he's malicious or he's slow or he's not in sync with the network, we can disregard this guy. And this is what a 51% attack looks like. We're assuming that if you could gain control of all these nodes, then everybody does CDE, that's the consensus, so that gets sealed. So we know it's ABC, right? Cool. Now this would take like 1 second, 2 seconds. It doesn't take that long to do. This will take like a second to do. It's really not that hard. So what happens to the other 9 minutes? Let's even give the benefit of the doubt. So the internet is slow today. It takes a minute to essentially transmit and compare all this stuff. A minute is a very long time.
Does location matter?
Well, location, like if you're in China, maybe the ping is like
A little slower, but that's
200 milliseconds.
negligible.
Negligible to like 10 minutes, because we're talking about. Yeah, I mean, it is sort of, but it's negligible in this instance.
So it's just like an advanced verification system?
Yeah.
Okay.
So essentially, 1 second, ABC, now what do you do for the rest of the time? So now you start mining it. So if Bitcoin didn't have any mining, the throughput would be phenomenal, because every second is going to have an entire block of transactions with it, which is 3 per second, and then there's 60 seconds in a minute, and there's 10 minutes, so that means that there's 1,800 transactions per second if there was no mining. And we're assuming that this is like 1 second, which, you know, there's ways by which we could increase that, but that's a simple math way of explaining this. So what happens to the other time? So you have to introduce Bitcoins into the network, and you have to do that fairly. And the idea is that it has to be done at a rate that is the same over time. So if there are more people using the network, you know, maybe in the beginning 3 people were using the network and they did 3 transactions a second. And then you'd say, well, every time a block's produced, or let's say there's 3 transactions in a block, 1 a second. But if there's 6 a second, then you producing 2 blocks a second. You see how that works because it's a fixed size. Vice versa, if this was a variable size, those big chunks would still be distributed. But it's not. Okay. So we have this. And, God, what was I saying? I lost my train of thought.
Pretty much 6, and then you're talking about, I don't know where you looked at.
Yeah, what happens to all the time, right? So basically, we're going to be mining this, and this is through proof of work. Oh, right, distributing rewards. That's right. That's what I was talking about. Got it. So essentially, what happens is you want to introduce cryptocurrency into a system at a similar rate. And if you're producing blocks at a time that is irregular, you start giving more of a reward. So if like you're producing blocks faster, you are giving out the reward faster, and that doesn't work for the deflationary aspect of cryptocurrency. So the developers of Bitcoin said every 10 minutes there wants to be a block. So how do you make it so that there's a block is produced every 10 minutes? Well, okay, so now we're going to do proof of work. So essentially what proof of work does is you essentially hash this block, right? We did it once with ABC. But this is where difficulty comes into place. So that's not valid, right? Because it only took us 1 second. So we need to do something with the other 9 minutes. So we're just going to do proof of work. So difficulty is essentially something saying that given a hash of a certain length, it has to start with a certain amount of leading characters. So we're just going to say it's A's. And this would be the solution. Now this is hard to do because to have 5 A's in a row, you have to go through how many different combinations. Like the probability of you getting that is very low. So you have to modify the block a little bit and then hash it again. And because you can't predict what a hash looks like before you hash it, you have to try it out a whole bunch of times. So you'll add 1 to this, right? And so it'll be a block plus 1. And then you'll hash that. And chances are that it doesn't work, right? And then you'll add 2, you'll add 3, you'll add 4, and you hash it each time, and you keep on doing that until you get a hash that's like this. So the actual content of the block's not changed, just this little proof, right, that you tried and worked on it to produce this. This is what proof of work is. That's your proof, this is the work. And you can tell it's the work because it has 5 leading A's. Very easy, right? But this is not doing anything in terms of any of your transactions. This is after we already decided what was in the block. So the transactions are already determined. This is just to decide who gets the currency. Makes 0 sense. I don't get it. Yeah, does that make sense?
No, well, it makes sense what you're explaining. Like, the concept doesn't make sense.
Yeah, that's what I'm saying.
Waste of time.
Yeah, so a waste of energy. Right now, Bitcoin is taking up more energy than Ireland.
Yeah, we were actually talking with someone today about the NVIDIA stock just skyrocketing due to all the miners buying the processing power.
Yeah. So, like, what difficulty really is like, it will be like, the network is like 2 terahashes difficult. What does that mean? That means that a block takes about 2 terahashes, and a tera is what, a trillion? So, that's a mega, that's a giga, that's a tera. This many hashes. So when I was like, oh, you try 1 and then hash it, that's 1 hash. And then you try 2 and then you hash it, that's 2. Then you try 3 and you hash it, that's 3. What this difficulty reflects is that with all the miners right now trying and doing that, because he could start from 10 and work his way down. He could just be trying random data. I could be trying random data too. Yeah. There's no way that we are coordinating which nonces we are the nonces of proof. What proofs we're trying, there's no way to coordinate. I mean, maybe there is, but it doesn't matter. Yeah. You just kind of let this thing run. This number indicates how many hashes the entire network does in 10 minutes, because 1 block every 10 minutes, right? And it goes to 1 miner. So there you go. 2 trillion hashes. Why? And this doesn't, we hashed 2 trillion times, didn't change the transactions inside the block. That was done within the first 5 seconds of this block being produced, right? And so that's Bitcoin. Yay.
Yeah.
So this alternates based on how many miners are in there. So if more miners are added, that means more hashing power is added to the network, which means instead of saying we can process more, it means we can do pointless work more, and we have to adjust this because we don't want that fixed block time to change because we want only one block to be produced every 10 minutes. I don't get it. But so let's say a whole bunch more miners join, and now it's 2.1 terahashes. Doesn't matter. Now it's just harder. So it's like, it's stupid. What we're doing is different. So if we go back to this node thing, this is kind of like delegated proof of stake. I'm not like necessarily basing this completely on proof of stake, rather what is the easiest and fastest way to validate these blocks. So you have all these nodes. These are full nodes. So this is a DPoS type of system. So you have these validators or these sealers of the block. Now, in the system, before there's a degradation of the performance, it's about 128 actual delegates. And now these delegates can be voted on by other committee members, which would be, in fact, the witnesses, right? Now these people don't actually contribute anything in terms of like, I'm gonna put these in the box.
Beautiful.
Alright. These people don't contribute anything in actually like sealing the blocks, right? What they do is they keep a record and they have eyes on these people and they are seeing what everyone's doing, right? Because these people are the important delegates. So a transaction will come in, right? And then this transaction will propagate throughout the network. Everybody gets it, right? And it starts to fill up this queue, right? So boop, 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 boop. This is the block. So fill these transactions up to the top. When this is hit, instead of hashing and finding some pointless proof, how many we gotta do? Instead, we just are gonna go and get it signed by every single validator in the chain. So we're just gonna do 128 signatures, which is far less than 2 trillion hashes. And so this means that we can process blocks quicker and faster, which means our throughput is much faster. And why do people care about proof of work? They don't. It just works. And so that's why people use it, because it's the status quo. It's like, why are we doing cryptocurrency in the first place? It's against the status quo. I mean, there's established rules, and until somebody questions it and says, is this the proper way to do it, you just kind of do it because that's what works. It's just how we've been doing it. It's worked for 8 years, so let's keep on doing it, right? So essentially, instead of that, we have transactions coming in. They get basically added to this roster queue of everybody observing the network. There's 128 actual sealers or validators of that. So it goes around and essentially step 2, right? The block is full. These people then hash it, so ABC. They compare it with everybody. And they say, cool. And now these people also will do that, these witnesses. So if these people start colluding, they can vote them out. And they can say, you are not calculating these blocks. You are voted out. And this way, it keeps the system from having those attacks. Because, let's say a power at B is somehow manages to get all the votes of the witnesses and starts manipulating this shit. They can essentially vote them out. There's nothing we can do about it. So what then happens is we agreed upon it's ABC, right? Then essentially what happens then is everybody signs the block and publishes it out into the quorum. And everybody else is subscribing to those echoes. So I get the block and then it's ABC and I sign it with my private key, which nobody can replicate. And I say, my signature says DEF. And so it goes back to everybody else. And these people validate and they make sure because they can use my public key to then say, yeah, I actually did sign that message. And this gets turned into a list of 128 of these signatures, right? So it's think of them as actual signatures. These committee members sign off on this, right? This whole package is then hashed and then propagated back to everybody. and then that hash. If that hash is correct with everybody, that means that all the signatures were checked, they were validated, they approved, and then it gets sealed. And then you work on the next block. And this can happen asynchronously, and it just churns through it. And this seems more complicated, maybe, right? Maybe it seems more complicated, but it's a hell of a lot less work in terms of what's actually being happening on like a processor level and a power level than Bitcoin. This is like much cleaner, much sleeker, much simpler, and it makes sense. And it also does tie into these new paradigms that we're seeing. I mean, DPoS seems to be what people are doing. We have Lisk, we have Arc, I think Neo does DPoS, BitShares, these newer era, this is what people are doing because they say, why are we wasting all this energy? Why am I just, you know, I have a space heater that's mining Bitcoin, you know, it's just blowing out power. And this is what's stopping people, because what also this means is that transaction costs are so minimal because there's no work. I mean, what's a good example? Any web app that you use, why are those free? Why is Facebook free? I mean, they sell your data, right? But initially, they were able to put out a free product, and they were able to support that without really that much effort. And I could spin up, you know, for 20 bucks a month, I get a little server on a network somewhere in a data center, and I can put up, you know, my apps. I can I had an auto trader app that was like doing work, and it was like analyzing the markets and doing all this stuff. That is about how much work is required to run one of these nodes, because all it's doing is networking with each other. It signs the block message. It just keeps a list of these. It signs it and propagates it out. It listens for things to come back. It then signs that and listens for all the other signatures to come and validates them, hashes that and signs it out, and then confirms. That's not that much work. I mean, a database does more work, potentially. So this is so lightweight that the transaction fees are just destroyed. There's no point. And because to do a transaction, you actually do have to do a small proof of work. Whoa, Stuart, you hate proof of work. Whoa, let's read the actual Hashcash paper, which Bitcoin was supposed to be based off of, and then let's make that assumption. Hashcash is an anti-DDoS or denial of service attack, distributed denial of service attack, by which by sending a whole bunch of requests at a network, you can load it and destroy it because it becomes too inundated with spam. The Hashcash mechanism says with a fixed difficulty, so it's like fixed. Maybe it's 3,000 hashes, right? It's always going to be 3,000 hashes. It doesn't ever go up beyond that. And if those hashes are ASIC resistant, like Bitcoin Gold or Zcash with Equihash, things like that, you can make sure that people aren't cheating the system and hashing faster than anybody else. You can prove that a transaction will take about a second of computing work. Great. And that prevents spam for this entire network. Completely streamlined. So the mining aspect is a fixed difficulty. It doesn't get any worse. And it's on the user who's using this. If they're using the network benevolently, then it's not going to be an issue. If they're trying to hack it, then that's when that barrier comes into play. Because if you're trying to do, 1,000 different transactions in a second, I mean, then it might get a little bloated, right? And so that's where things get interesting. But if you think about this in the context of what it's being produced as, this is a centralized router. I don't want to say centralized because the blockchain is decentralized itself, but it's centralizing these other decentralized systems and saying, look, this is the pass-through network. So it's not like you're going to be spamming a whole bunch of information. It's you're using it to pass through the chains. But yeah, that's about it.
Cool.
Any questions?
I understand.
Oh, wow.
Thank you, Stu.
No problem.
But yeah, if any of you guys made it this far, let us know if you want other things explained. We'll be pushing out more dev videos as time goes on. And if we have any business requests, I'll be handling those types. But other than that, thanks, Stu, for walking us through this. And yeah, we'll be pushing these out more often, guys. So, cool.
Yeah, thanks.
All right, thanks, guys.